Perfect.
Okay. Yeah, thanks everybody for, and especially the organizers for giving the opportunity to discuss for you some of the recent results of the of heavy ion physics at the highest energy frontier. So I take that to mean at the LHC. I will try to cover some of the kind of general outline of the physics, but then also a number of recent results. So as you've already seen from Mike's talk and Peter's talk, what we study in heavy ion physics is a system that evolves, that produces a very high density liquid quark-gluon plasma liquid, which then expands and falls apart. And when we think about the collisions, we also have different observables that measure the different stages of this evolution, which you see sketched at the bottom of the slide here. And I would say the core of the field is studying the properties of this quark-gluon plasma matter, things like the equation of state and transport coefficient, and I'll go into that in the slides. But there's also a very important part that is about studying more dynamics. So for example, hadronization or interactions with the quark-gluon plasma or rescattering in the final states. And I'll also give a few examples of that. So to start with the let's say, transport coefficient and to connect a little bit to what Mike has been showing. So if you think of the initial state of a collision in position space, so you see here a sketch where you have two nuclei colliding, and we can analyze the shape of the collision region, and in a real nuclear collision, this shape will not be smooth, but will actually be there will be hotspots which come from the protons and the neutrons, which are kind of discrete particles within the nucleus. And it turns out that the shape then is not, has many irregularities, and it means that while the kind of the dominant shape is an elliptic shape, there are also triangular and even quadratic and higher order components which are sketched by these contours. So what you can do is you can take this density profile and make a Fourier transform to characterize the different shapes that are in there. And then in the collision, this is the starting point, but this leads to density gradients, which then in the expansion transform this configuration space anisotropy into momentum space anisotropy that we can measure. And to illustrate how we measure that, on the right-hand side, you see now an azimuthal distribution of a single event, of particles in a single event. At the LHC, you have so many particles that you can already see these anisotropies in a single event. So the bumps and troughs that you see are really coming from momentum space anisotropy. And of course, then to make it more precise, what you do is you sum over many events, and you see correlation plots like the one at the bottom, which then allow you to get these similar Fourier coefficients, but now of the final state. And to illustrate that, I show here just a sample of those measurements. So what we normally do is we plot this as a function of transverse momentum, and then you see here the amplitudes of the second coefficient for many different particles. There's a characteristic mass dependence that you can see here at low PT, where heavier particles have a later onset of this elliptic flow, which is has to do with the fact that it all comes from a collective velocity. And one can extend that to even to deuterons, which Peter also mentioned are produced in the collision, and other light nuclei. And then we can also do this measurement for the higher order or the higher harmonics, the third and the fourth harmonic, and these are analogous plots for that. Now, a lot of this, these studies have been going on for a while, so we have a very complete set of measurements. What is relatively new is that you can now do a systematic comparison with the expectations with a model and extract knowledge about the system from that. So that is one example. The main example is shown here in this slide, where you see on the left, you see the measurements compared to calculation curves. There are two panels which have this azimuthal anisotropies. Other things that enter are things like multiplicity and the total transverse energy, or the mean PT. And then in the middle, you see a reflection of the constraint parameters of the model. So in total, in this model, there are 14 parameters. So some are correspond to the initial state, other correspond to the medium properties, and others are kind of technical parameters of the model. And here you can see, if you zoom in, how the measurement constrains all these parameters. And somehow the core parameter or the core information that we then extract from this is shown on the right, which shows now the viscosity as a function of temperature at eta over S to make it dimensionless. So the viscosity over the entropy density as a function of the temperature, and the orange band is the temperature dependent viscosity as determined from these measurements with its uncertainty. And you can see that the values are very small and that the temperature dependence is quite small. And when I say small, you can compare that to water and helium, which are of course atomic materials, so they have a very different length scale. But this shows you that the quark gluon plasma has in fact very strong interactions, somewhat counterintuitively. Low viscosity corresponds to a short mean free path. I think it's really impressive to see that we now can extract these type of properties of the quark gluon plasma from a set of measurements. Now, it doesn't stop there. I mean, one thing in the same vein that I would like to emphasize is that we've seen similar effects now in proton-proton collisions. Also, actually, already early results from the LHC showed this to us, and it was a bit of a surprise. It's illustrated here by looking now at two particle correlations. On the left, you see results from heavy ion collisions. In the middle, you see low multiplicity proton-proton collisions. On the right, you see high multiplicity proton-proton collisions. And you see that these high multiplicity collisions look actually a lot like central lead collisions. And there in particular, there is this near side ridge. There is a correlation which is long range in the longitudinal direction in rapidity. And on the near side, so at a small angular opening angle. And that is a signature of something that comes from the initial state, because the areas in the collision that are far apart in longitudinal direction come from different longitudinal spots along the collision zone. And so for this to be correlated, all these longitudinal spots have to talk to each other. And so the most natural mechanism for this is something that comes from initial geometry and then transfers this anisotropy to the final state. But this led to quite a discussion, because of course in proton-proton collisions you don't have a large system. You don't expect to have time and density to produce a fluid that can build up pressure gradients. And one of the answers to that conundrum is shown in this slide. So it turns out that with relatively few collisions, you can already get significant flow. And here on the right, it's a theory calculation that explores that. And you see the elliptic anisotropy as a function of the system size expressed in the number of mean free paths. And you see that from basically zero system size, the azimuthal anisotropy starts to increase until it reaches at a few times the mean free path. It starts approaching the hydrodynamical limit, which is what you get for a full fluid. And the way this works is sketched on the left, where you see different kind of particle production points within the proton-proton collision in this case, which each emit particles in an azimuthally isotropic way. But then in the course of the evolution, and that's what you see in the middle, the system is not locally isotropic. So what you find here in the middle is that the particles tend to move in the horizontal direction in the sketch. And when they collide, they isotropize. So collisions will have a tendency to move from the horizontal direction to the perpendicular direction, to the vertical direction in this plot. And that gives rise to this flow-like effect. And so we now understand, at least qualitatively, how this can arise in proton-proton collisions. And to show you a few kind of recent developments on this, I wanted to show this summary of measurements of this same effect now with heavy flavor quarks. So you see on the left, you see a summary which contains light and heavy flavor quarks of this V2 effect in proton-lead collisions. The red points are the charm measurements, which seem to participate in the flow. And on the right, you see that from semi-leptonic decays of charm particles. And then there's also measurements with beauty, the even heavier quarks, so the blue on the left and the red on the right. And there it seems that there is no flow effect. So it seems that we found the kind of the limit of how much flow you can build up. And it seems that there is a mass dependent limit and that the heaviest particles do not participate. Although I think with more statistics, we'll get more precise measurements and we might see whether it's really zero or just a lot smaller again. So that concludes this discussion of let's say, bulk properties of the quark-gluon plasma. And now I would like to go to what we call hard probes of the quark-gluon plasma. And this refers to rare processes in the collision, which then produce particles which then traverse through the quark-gluon plasma and interact with it. And in that way, they probe the plasma. You see this animation to illustrate that. The yellow lines are the particles propagating through the plasma. And for hard probes, the key point is that there's a large scale involved, which is much larger than lambda QCD. And that means that the formation is very fast. And that means that production process can be calculated independent of the medium formation. And to illustrate that that's really the case, on the next slide, you see the nuclear modification factor. That is somehow the simplest measurement you can do in this area, which is basically measuring the transverse momentum spectra, which are shown on the left for proton collisions and lead-lead collisions at the LHC. Now there's a volume factor, which is called the number of binary nucleon-nucleon collisions, which you have to take out to compare the two. And then when you do that, you get this figure for the hadrons. But let's first turn to the middle where we have the ratio now, so the nuclear modification factor of the lead spectrum and the PP spectrum with the normalization for photons. And there you see that this nuclear modification factor for photons is equal to 1, which tells us that photons, as we expect, do not really interact with the quark-gluon plasma. So they follow this geometrical scaling with this number of binary collisions, and then they escape without interacting. However, if you look at the plot on the left, you see that for charged particles, there is a change between proton-proton and lead-lead. And we normally plot this nuclear modification factor, which you now see on the right. And you see that the ratio is much below 1, which is a sign of energy loss. There's a shift of the spectrum to the left. And if you take the ratio, it's a shift down. It's a nuclear modification factor below 1. And we can now analyze this, and in much the same way as we did for the flow measurements, we can extract the relevant physical parameter. And I'll go through that in a bit. But before doing that, just one feature I would like to point out is that here at low PT in this nuclear modification factor, you see this non-monotonic behavior. That is actually related to the flow effects that I've been talking about before. So when I talk about parton energy loss, we look at this region above 5 GeV or so, where that is the dominant process. Now this has been all measured for light flavors. I would like to show you also the corresponding results for heavy flavor. And not only the nuclear modification factor, but also the azimuthal anisotropies. Before doing that, I wanted to emphasize that there are kind of two mechanisms to get this azimuthal anisotropy. One is the expansion of a plasma or a fluid that I talked about in the first slide, which is sketched on the left. The other is from the parton energy loss, from interactions of hard partons or quarks, heavy quarks with the medium. Those are produced isotropically, but then they go through the quark-gluon plasma, which has a long and a short axis, and they lose more energy when they fly along the long axis, leading to a reduction of the yields along that axis. That gives a very similar azimuthal anisotropy. And the physical parameter that governs this azimuthal anisotropy and the nuclear modification factor is the Q hat, which is shown in the formula on the right. So the energy loss is proportional to this transport coefficient Q hat times the length through the medium squared. Now, on the next slide, I show then the nuclear modification factor for this time heavy flavor, which looks, in fact, qualitatively very similar to the plot for light flavor. And I'll comment on that in the next slide. And the elliptic flow, the V2, the azimuthal anisotropy, also for heavy flavor, where you see that up to very high PT, there is a clear anisotropy, which is then driven by this difference in energy loss in and out of plane. And you see a number of model calculations. Many people are trying to describe this process with slightly different approaches. So that gives us a very good systematic view of what we understand and what we do not yet understand about these processes. And to summarize that, I would like to show you this plot, which is the extracted or the determined nuclear transport coefficients, which are now determined from fitting the data as we saw in the previous slide. On the left, you see the diffusion coefficient, which governs the behavior at low PT. This is a spatial diffusion coefficient. And on the right, you see the Q hat, this transport coefficient that I talked about that drives the energy loss at high PT. And the red curves are from a fit to the data. And also here you see that with the data that we have and our different inputs on the properties of the collision and of the medium, we can determine these transport coefficients with a reasonable precision, and even their temperature dependence now starts to come in focus. In the figure, you also see comparisons to other model calculations, which, as you can see, are in the same ballpark, although there are sizable uncertainties, and even to lattice QCD calculations for the transport coefficient. On the right, there's also a corresponding determination of this Q hat, this transport coefficient from light flavor measurements. And it's very nice to see that they fall on the same curve. So this means that we now have a quantitative understanding of this energy loss process for both heavy and light quarks, and that it actually, we can describe both this REA and the V2, the azimuthal anisotropy, with these models. So there, I think the net is closing in on these properties of the plasma. So what's going on now in that subfield is that we are also now measuring the next heavy quark, which is the beauty quark. And the interesting physical effect there is that when you have a beauty quark at not so high PT, the velocity of that quark is not quite the velocity of light. And that leads to a suppression of the energy loss, the so-called dead cone effect, which is a limit on the radiation angle, which comes from this finite velocity. And we see that in the results. There are plots from 3 different experiments, but you see on the left, for example, the non-prompt D mesons, which come from beauty, have less suppression than the prompt D mesons, which come from charm. And the same for the non-prompt J psi, which come from beauty. And in the CMS figure in the middle, you see very similar results. So all of those show that at not too high PT, the beauty energy loss is smaller than the charm energy loss, in line with this dead cone effect. I will later also comment on the same effect, which is actually also visible in PP collisions, and we have an even more direct measure of the angular distributions. So that to do that, we look at jets. So jets are the particles coming from the fragmentation of high momentum partons, quarks or gluons, or heavy quarks. And then they have an experimental signature, which you can see on the left. You see in an event display a clear concentration of energy, which comes from the fragmentation of one hard parton. And this is an interesting tool because it allows us now to study the angular distributions of the radiation or the energy loss. And you can, for example, distinguish in-cone radiation, which does not lead to a suppression of the jet yields because it's counted in the jet energy, but to a modification of jet structure, and out-of-cone radiation, which leads to a suppression of jet yield. And that you can use then to study, to benchmark your understanding of the energy loss process itself. And before going there, I wanted to show the dead cone measurement that I just talked about. So you can also use these substructure jets and substructure measurements to look at, to search or to look for the dead cone effect in PP collisions. And this shows the main measurement that we have for that. So what is done here is that you follow prongs inside the jet, which follow basically the showering process, and you can then plot the angular distribution, which is shown in the middle. The axis is such that large opening angles are on the left, and you can compare light and heavy quarks, or light flavor and heavy flavor, by looking at the D-mesons in the final state, and make a ratio, which is shown on the right. And there you see that the radiation at small angles, so on the right in the plot, is suppressed for heavy flavors, and that is exactly this dead cone effect. And so this is a kind of the most direct way of mapping that the radiation angles with the substructure measurement, and it shows an imprint of this dead cone effect, which is, I think, very impressive. Now with that, I would like to go back to the discussion about energy loss. So one way that you've probably seen before that we can look into this is by looking at dijet events where you have a pair of jets back to back, and as shown in the event display on the left. And if you have only two jets, what you expect is that they balance in the transverse momentum, that the near and the away side jet have similar PT. And you can see in the middle where we show the momentum balance of in PP collisions, that indeed most of the jets have a momentum ratio. This xj is a ratio of the momenta of the two jets, which is close to 1. And then there is a tail to lower values, which comes from 3-jet events and cases where not all the energy is contained in the reconstruction. But if we then compare that picture to what we see in lead-lead collisions, this is shown on the right, you see that there these asymmetry distributions are much broader, meaning that there are many more cases where you have a very asymmetric dijet. For example, the black points, you see almost as many cases where the recoiling jet is only half the energy of the leading jet. And if you then go up in energy, that is what the different colors are, and that is the new result in this plot. You see that this energy balance becomes slowly restores, which shows that the relative effect of this energy loss decreases as a function of energy, and that you can expect at this moment qualitatively with expectations. This is in line with the Bremsstrahlung expectation, where the energy loss does not increase much with energy, so it goes with the logarithm of the jet energy. And it's, for example, different in a strong coupling picture where the energy loss will be linear with the energy. So another area in the same sub area is another type of thing you can do is to look at jets with larger and larger cone radii. Now to look really at this angular distribution that I talked about. This shows some recent results in that area. So one is the measurement of nuclear modification factor with small and large cone radii in the middle. And on the right, it's plotted as a function of cone radius. And what we see is a relatively weak dependence on this cone radius. And you see also the model curves in the plot on the right-hand side, which actually show two opposing effects. One is that as you grow the jet cone, you catch more and more energy, the REA goes up. But the counter effect is that as you have broader jets, you can have larger energy loss because you have more prongs in the jet. And it turns out, according to the measurements now, that these effects counterbalance each other somewhat, and the net effect is a rather moderate increase of this of REA with the jet, with the radius. Now, as a last last topic, I would like to go a little bit towards this dynamics that I talked about in the beginning, looking at a few things that pertain to hadronization and rescattering, which is the final state of the final part of the development of the collision. And one of the things that is interesting to think about there is whether particles are formed via fragmentation type processes or via coalescence type processes where quarks come together and form a hadron. I won't have time to go very deeply into that, but I'll show you some of the recent results. So one of the areas we are now measuring, we're having a lot of results, is the measurements of heavy flavor baryons. And this is of course interesting for this coalescence picture because you have 3 quarks, and if you compare to mesons which have 2 quarks, you can do some accounting. The basic observation that we've been making for a while now is that the lambda C to D ratio, so the baryon to meson ratio in proton-proton collisions is much larger than it was in E plus E minus. So there is some effect even in proton-proton collisions that enhances the baryon production at moderate to low PT, so below 10 or so GeV, which is the left half of the plotters. Now, recent updates on this is that we've now measured this also for other charmed baryons, and they show very similar trends. So for the sigma C and the Xi C, the numerical values are a bit different, and we need to do a more thorough comparison to model calculations to understand really what this means quantitatively, but it shows that this enhanced baryon production is really a general feature of in the charm sector at the LHC. And that also means that if you're wondering about, for example, the total charm quark yield, you have to start taking this into account, because at the LHC, about 1/3 of the charm quarks end up in baryons versus about 6% in E plus E minus. Now, we've also measured this in heavy ion collisions, and you see some examples here. So on the left, you see the PP results in green, and then heavy ion results for the lambda to the baryon to meson ratio in blue and red. And you see that despite a much larger system, the increase in this baryon to meson ratio is not very large when you go to lead-lead. And so far, this is in line with expectations from coalescence models, some of which are drawn in the right-hand picture. I think, as I said, this needs a little more careful look, but that is where we stand at the moment, and that probably has to do with the overall charm density in the collision. Now you can take this one step further, and you can look at the Chi-C, the new tetraquark state that we now measure also in PP collisions as a function of multiplicity, and even there's a first measurement in lead-lead collisions. Now I just wanted to highlight that here in the middle you see a model comparison where this measurement also gives us information about the nature of this state. So for a tightly bound state versus a hadron molecule, deformation rates are quite different, and according to this paper, the data are really mostly in line with this compact tetraquark interpretation of the state. Now, finally, thinking about this final state effects, we can also actually use the heavy ion collisions, or in this case even PP collisions, as a laboratory to study interactions between hadrons. And the way that is done here is with femtoscopic techniques, and where you measure momentum correlations, and they again give information about spatial correlations. So if you know the space-time distribution of the production points, for example, by measuring them with identical particles or with particles for which the interaction is very well known, then you can actually use this to study the interaction between unstable hadrons like the proton and the Xi baryon or the proton and the omega baryon. And here you see 2 results in that category. So the data points are these correlation functions, and then the lines are predicted correlation functions with different potentials, interaction potentials. And we see now that these measurements are very close to expectations from lattice QCD. So this allows us to test lattice QCD calculations of these interactions in the hadronic state. Now, before summarizing, I wanted to give a very brief outlook to the future, echoes some of the things that Peter already talked about. So at the LHC, we are currently at a long shutdown. And in particular, Alice is doing a lot of upgrades. I'm familiar with that because I am working in Alice. We are replacing the inner silicon tracker, the TPC. There's a new muon forward tracker with also silicon technology, upgraded readout and online processing. And actually there's more that's not on the slide because almost every subsystem, as Peter said, is being improved to achieve a higher readout rate. And the goal is then in round 3 and 4 to collect 50 to 100 times more minimum bias data, as well as a large increase in total luminosity, which will also be beneficial for Atlas and CMS and LHCb to some extent. Now looking forward, there are also future upgrade plans for Long Shutdown 3. Long Shutdown 3 in 2025 is when Atlas and CMS will do their main upgrades. But also in Alice, we plan to take a next step with with an ultra-thin tracker, which improves further the dilepton measurements and also the heavy flavor measurements, and a forward calorimeter, which measures very forward photon production. And that gives information on the small x gluon density in the proton, but in particular also in the nucleus, which is also an interesting connection to cosmic ray physics, where some of these uncertainties actually matter in the predictions of, for example, atmospheric neutrinos. So that brings me to the end. I won't go through all the points, but I hope to have shown you that in heavy ion collisions, we can study now in quite some detail the properties of the quark-gluon plasma. We get information on viscosity and transport coefficients, but we also look at in more detail at dynamics of this parton energy loss, but also of hadronic processes like hadron formation and these interactions between unstable hadrons. And with that, I would like to thank you for your attention.